Hi everyone, in this video we'll learn the AC-DC conversion. The AC-DC conversion are commonly called as rectification. The devices are rectifier. The diodes are used to pass forward current and block the reverse current. The easiest way to do this job is to use one diode. The topology looks like this. The output looks like this. We only have the positive half of our input. If the input VAC is Vm times sine omega t, then our average Vout is Vm divided on pi, and our RMS value of Vout is Vm divided on 2. To improve the DC quality of Vout and Iout, a capacitor is applied. After apply a voltage, the output waveform of voltage will look like this. And this is our delta Vout and the average value of Vout. And the average of output voltage can be calculated as Vm minus delta Vout divided on 2. The capacitance can be designed by using the delta V value. So our Cout is equal to average Vout divided on delta Vout R times frequency. We don't want the whole half cycle wasted, so the full diode bridge is created. The output voltage looks like this. Now the average and RMS value of the output voltage is 2 Vm divided on pi, and RMS output voltage is Vm divided on square root of 2. So same with half-wave rectifier, we can use a capacitor to smooth the output voltage. After we apply the capacitor, our average output voltage is Vm minus delta Vout divided on 2, and our capacitance is also calculated by using our delta Vout value. Average Vout divided on 2 delta Vout are F. After apply the capacitor, the waveform will look like this. When the capacitor designed in good size, the output is maintained in good quality. However, when we look at the input current, we will find the input current became to this. This is because we use capacitor to maintain the voltage, so the diodes are only conducted in very short time. This will give us a very high distortion in input current. So from all the converter we learned before, we know that the inductor is used to smooth the current. So we can add an inductor at the output side to make our current smooth like this. When we put an inductor on, our average output current is 2 Vm divided on pi times R, and the inductance is calculated using current ripple. The detailed derived process will not discuss here, but I will let you know the inductance is Vm divided on 14.92 times delta I times F. The better way to both smooth current and voltage is using Lcl filter. The average voltage and current using Lcl filter is average current is 2 Vm divided on pi times R, and average output voltage is 2 Vm divided on pi. we use the same inductance calculation as we only use L filter. Our L is Vm divided on 14.92 delta IF. The capacitance current is smooth after inductor, so the calculation of capacitance is different of only using C filter. So our C value equals to delta I divided on 4 pi f times delta V. Every application involving inductor will meet the CCM and DCM condition. The boundary is same is when our average inductor current is equal to delta I divided on 2. So the critical resistance can be calculated as 4 Vm divided on delta I times pi. If the load is larger than this value, the rectifier works in DCM. In DCM, the average of output voltage and current is different. You can use simulation to find out this. The 4-diodes rectifier is based on passive diodes. We cannot control the output voltage, so we can replace the diodes by thyristors. The topology looks like this. By control the thyristors, we can scale down the output voltage. The operation is called phase control. If we look at one thyristor in here, if here is a diode, our turn-on pattern looks like this, and our output voltage looks like this. But with thyristors, we can delay a phase of alpha like this. So the output voltage will become like this. Because the waveform is chopped, the average and RMS value of output voltage are related to the alpha value. So they are the average of output voltage is Vm divided on pi times 1 plus cosine alpha, and RMS value of V out is Vm times square root of 1 on 2 minus alpha divided on 2 pi plus sine 2 alpha divided on 4 pi. The alpha also influences the power factor, though the power factor can be calculated by square root of 1 minus alpha divided on pi plus sine 2 alpha divided on 2 pi. The angle shift, aka the alpha value, can influence the voltage conversion ratio, and the power factor looks like this. The higher alpha goes, the lower conversion ratio we have, and also the lower power factor we have. So same way the 4-way rectifier, we can design the Lcl filter for our active rectifier. The design process is same with 4-way rectifier. In this video, we learned 3 types of rectifier, the easiest way using half-wave rectifier, and then we learned the 4-wave rectifier. And by adding the control to the rectifier, we also learned the active rectifier. So this is all about today's video. Thank you for watching this video. We will see you in next video.